Hi, I'm Norman Wildberger. In today's video, we are going to solidify our understanding of the spread between two vectors. We have seen that this is intimately connected with the notion of determinant, which expresses the area of a parallelogram. Today we want to connect this with linear algebra and move towards understanding this beautiful threefold symmetry called chromogeometry, which sort of lies at the heart of planar geometry. Okay, so here's what we have discovered so far. That if we have a vector v, which is AB, and a vector w, which is CD, then the spread between them, this s here, can be expressed with this formula here. It's AD minus BC all squared over the product A squared plus B squared times C squared plus D squared. What's in the numerator here, this AD minus BC, is just the area of this parallelogram, actually the signed area of this parallelogram. And we introduced the idea of a cross product in the planar situation. We said that this number could be regarded as the cross product between V and W. That's a very useful kind of thing that's a little bit different from the three-dimensional cross product. It's a number then that's associated to two vectors, which just tells you what's the area of the parallelogram that they span. Now the fact that this is a signed area doesn't really figure because we end up squaring it, so we end up with something positive in the numerator anyway. And the quadrances here are in the denominator, so that's kind of a normalization. So geometrically what we're doing is we're taking these two vectors and we're looking at this parallelogram, taking the square of its area, and we're dividing that by the product of this square area and this square area. Okay, so it's really a normalization of a squared area. In fact, it's geometrically perhaps the simplest kind of number that you could associate to two vectors, which ended up not really depending on the scaling factor. So if you scale the vectors v and w, then this quantity does not change. The quadrants, of course, is the fundamental concept in rational trigonometry. And we can also interpret it here as also a cross product between vector v and what we might call v super b, which is the rotation of the vector v. So if v is ab, then v super b is minus ba, and that's a rotation by a quarter of a turn. So physically, if this is v, then v blue would be up in this direction here. And I'm drawing the square on this side, but it's probably actually a little bit more honest if I drew it like this, but then it would overlap the current diagram. For the w, same story. The w is there. The wb would be this vector here. So we'd be talking about the area spanned by this w and its blue rotation. So very nice formulas, and we want to look more carefully now at the nature of this expression and then ultimately move to the red and green versions of it. So it's a very big step in 21st century mathematics to move from considering angles to considering spreads. Absolutely very crucial development. And let's have a look at how this spread is such a rich concept by seeing algebraically that it's full of life. So here is this quantity that we talked about, that we've just defined, and here is a very important fact about it that we've seen before, but it's well worth repeating. That it can be rewritten as 1 minus the fraction ac plus bd squared over a squared plus b squared times c squared plus d squared. Now what's appearing in the numerator here is also a kind of product of the vectors, but it's different from this cross product. This is called the dot product between the two vectors. So here it is right here. V dot w, in other words, the dot product between the vector AB and the vector CD, is this quantity AC plus BD, the product of the two first entries plus the product of the two second entries. It plays a very, very important role in linear algebra because it naturally generalizes so pleasantly to higher dimensions. Now this identity here is a consequence of what we might call Fibonacci's identity, which is this relation here. So if you take everything over a common denominator here, you'll see that it's equivalent to a squared plus b squared times c squared plus d squared equals, what do you get when you put this on the other side? ac plus bd squared plus ad minus bc all squared. So if it's been a while since you've verified this identity, please write out both sides, make sure that you believe it, that it's really true. And this is really the reason why this identity is valid. And it's really interesting because both of these are important formulas. So one wants to understand both of these expressions for the spread and how they reflect different properties of the spread. Here we have an area squared. Here we have a dot product, but there's a 1 minus this quantity here. Okay, so here's a few exercises for you. This first one is that showing that Fibonacci's identity on the previous page is equivalent to this alternate version. So it's quite like the previous one, except that now it's AC minus BD squared here and AD plus BC squared there. So these signs have both changed places. And show that this identity is actually equivalent to the quadrant's identity for complex numbers. In other words, that if z and w are complex numbers, then this is really the statement that the quadrants of z times the quadrants of w is the quadrants of z times w. And I remind you that the quadrants of a complex number a plus ib is the number a squared plus b squared. This is probably the most important identity in complex number theory, and it's really equivalent to this form of Fibonacci's identity. So make sure that you understand the point here. You'll have to remind yourself what complex number multiplication is there. Okay, so we're reviewing a few things that perhaps we've already touched upon in this course, but it has been a while since we've been doing some rational trigonometry, so it's great for us to review and get back up to speed because we are going to be doing a lot more very, very interesting rational trigonometry in the months ahead. Opening up all kinds of new vistas, very exciting stuff, and lots of opportunity, as usual, for people to make interesting contributions and discoveries yourself. All right, so rational trigonometry is an early theory. It hasn't been around for very long. A lot of mathematicians still don't know about it, so it's a great opportunity to get on top of things and forge ahead in a brand new, interesting direction. Now let's have a closer look at this dot product that we've just introduced. So this is another way of combining two vectors and getting a number. And we might call it the blue dot product because it's going to be just one of 3 dot products that are shortly going to figure in sort of a wonderful trilogy. But it's the familiar dot product that undergraduates learn about, and here it is again. There's the dot product of the two vectors, so it's AC plus BD. And by the way, if you want a bit of a review of these things, you can have a look at Wildtrig 46 to 51. Okay, so there's various properties of this dot product which are important to identify. Firstly, we want to remind ourselves or observe that the dot product is linear. And what does that mean? Well, it means that if you take, say, v dot, the sum w1 plus w2, so here are two vectors being added, you take the dot product between v and the sum, then you get the sum of the dot products v dot w1 and v dot w2. And that also happens on the other side. So if we take v1 plus v2 dot w, then we get v1 dot w plus v2 dot w. And also there's a linearity with respect to scalar multiplication, that if we multiply v by some number lambda and take the dot product, that's the same as taking lambda times the dot product of v and w. And that's also the same as v dot lambda w. So that scalar can be moved around from being in front of w to being in front of v to being in front of the dot product itself. Then three other important aspects of the dot product. First of all, that the quadrants of a vector is just v dot v. Okay, this is absolutely fundamental fact that the crucial metrical quantity can be expressed as a dot product of a vector by itself. In mathematics, we sometimes say that's a quadratic form. Another very important property of the dot product is that it's symmetric, that v dot w equals w dot v. You change the order, the dot product does not change. And a little bit more subtle, this property or connection with perpendicularity, that two vectors are perpendicular precisely when their dot product is 0. So this is another very important use of the dot product, is that it allows us to identify when two vectors are perpendicular algebraically. We just form their dot product, and if it's 0, they're perpendicular, and if it's not 0, then they're not perpendicular. So we need to talk a little bit more about this perpendicular property of the dot product. Students who take linear algebra courses are often taught that perpendicularity is defined in terms of the dot product. That we just define perpendicularity by the dot product being 0. But that's not really the whole story. So we can legitimately ask, why is it that we define perpendicularity via the dot product? Or in other words, why are these two things really equivalent? And the key is to understand that perpendicularity is a classical concept that really goes back to Pythagoras. It's Pythagoras' theorem that controls perpendicularity, or allows us to identify perpendicularity, going all the way back to Euclid, of course, and earlier. Okay, so here is the picture. There's a vector v, there's a vector w, and let's consider a triangle, because Pythagoras' theorem is relating to a triangle. So let's consider this vector that emanating from here to here. Now in vector language, if this is v and that's w, then this vector here is w minus v, because it has the property that if you take v and then you add w minus v, that combination is the same as just the single vector w. So we have a triangle here now with three sides, they're vectors, v, w, and w minus v. Okay, so what does Pythagoras' theorem say? Well, Pythagoras' theorem is saying something about the quadrances, that we should have perpendicularity there precisely when this quadrant plus this quadrant equals the hypotenuse quadrants. So here's the statement involved in Pythagoras' theorem, that QV plus QW equals QW minus V. And let's just look at this statement and rewrite it using what we know about dot products. Okay, so this statement is equivalent to the following statement. We've just rewritten this statement here because we've replaced Q of V with V dot V, replaced Q of W with W dot W, and replace Q of W minus V with W minus V dot W minus V. Okay, so now we have to stare at this. How do we expand this? Well, we can use the linear property of the dot product, allowing us to basically use a distributive law. This is really W dot W minus W dot V minus V dot W plus V dot V. There's four terms. And if we write out those four terms, you'll see that two of them cancel with the things on the left-hand side. The V dot V, which is the dot product of those two, and the W dot W, the product of those two, they cancel. So this equation here, this second one, is equivalent to this third equation, which says that 0 equals minus W dot V, that's product of those two, minus V dot W, which is the product of those two. Now, by the symmetry property, this and this are equal. So this is the same as minus 2 times V dot W. And if minus 2 times V dot W equals 0, that means that V dot W equals 0. So these statements are all equivalent just by using the linear properties and the symmetric properties of the dot product. That's telling us that this Pythagoras kind of relation is equivalent to the dot product being 0. Okay, so it's not really that we define perpendicularity to be this exactly. What we're really doing is we're noting that this property is equivalent to Pythagoras' theorem being true. And it's that allows us or justifies us to say, well, that's the same as saying that the two vectors are perpendicular. Okay, so this is an important point that often is skipped or not seen in linear algebra classes, okay? That there's really Pythagoras' theorem floating around here when we're talking about the connection between the dot product of two vectors and perpendicularity. And I might point out that in this argument, we are not really relying on the particular form of the dot product that we have. We're not relying on the fact that we have a blue dot product here. We're just relying on the linear and symmetric properties of the dot product. So the argument will also hold more generally. It will hold for other dot products as well. That'll be an important part of the story. Okay, so chromogeometry comes about when exactly we look at some alternate dot products. So we replace the familiar blue dot product, AC plus BD, with, say, the red dot product, which is AC minus BD. So this is a new way of taking two vectors and outputting a number. AB.CD is AC minus BD. If we use that definition of a dot product, we get a new kind of geometry, which we can call red geometry. It's a relativistic geometry. It's the same red geometry that we've already studied earlier in this series. And if we change things yet again by replacing what's here with AD plus BC, then we get what we're going to call the green geometry. So each of these geometries can be thought of in terms of being determined by a dot product, by the way of combining two vectors to get a number. This is by far the more familiar one to undergraduates, but you have to get your head around that there's something equivalent about these various things. This is just one possible choice. And algebraically, there's not that much difference between this one and this one and this one. A lot of the properties are still going to be satisfied. There's still going to be rich geometry. The red geometry is every bit as rich as the blue geometry. In fact, in higher dimensions, it's arguably even a little bit richer. And physically, relativistic geometry is just as important as Euclidean geometry, and arguably, in higher dimensions, it becomes even more important. That's the point of Einstein's special theory of relativity. Okay, so there's a lot of reasons to be a little bit wider in our understanding of geometries, and in this planar situation, it's a good place to start. And I also want to compare, in the same page, this other product that we have. The cross product, which I remind you is AB cross CD, is AD minus BC. This is looking a lot like these ones, but it's fundamentally different from these three. So you should think of these three as being in one box, and this as being in another box. This one is different because it's not symmetric. If you interchange the order of the vectors there, this thing changes by a minus sign. So it does not have the symmetry property. I remind you that the symmetry property is just what we used in that previous correspondence with Pythagoras' theorem. Okay, so that argument's not going to work with this one. So we do not call this a dot product, we call this the cross product. So we have three dot products and we have one cross product, and somehow these four things fit together in a very beautiful way. But what's really important is the threefold symmetry represented by these three. This is the phenomena of chromogeometry that's really only been around for, well, less than 10 years. That was my discovery, and I think it's one of the most pleasant things that I've been lucky enough to discover. It gets so rich, and it's really fabulously interesting and different from the geometry that has come before. Okay, so in our next video, we want to take the concept of spread, this algebraic, linear algebraic point of view, this connection with determinants that we've been talking about, and we want to transfer that understanding from the blue geometry to also the red and green geometries. That'll be very interesting. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.